And so the last talk, the last paper is by Srimanta Bhattacharya and Hegor Nandi, and the paper is entitled Revisiting Variable Output Length XOR Pseudorandom Function.
Thank you for the introduction. So this is a joint work with Hegor Nandi. Let us consider the basic problem.
Could you speak into the mic? I think.
Sorry. So let G be a set of size n. We are given a without replacement random sample of size sigma bar. And the goal is to generate a pseudorandom sample of size sigma. Whereby pseudorandom we mean that the total variation distance of the sample with a random with replacement samples should be negligible. So one approach is to consider the original sample as the pseudorandom sample. In this case, sigma will be equal to sigma bar. But we know that the distance of a random WOR sample with a WOR sample is approximately this much. So this is negligible only when sigma is smaller than square root of it. So the question that we try to address is, can we generate a pseudorandom sample for which the total variation distance becomes negligible even for values of sigma which are greater than square root of it. This problem is well motivated since the work of Bengali and others who considered this problem constructing PRFs from PRVs and found this Ruby Rakov backwards, referring to the famous work of Ruby and Rakov who considered the opposite problem. So there are some constructions, block cipher based PRFs, and there are some maps. The first set has Berger bound security, and the second set has beyond Berger bound security. So let us consider this method. We are given without replacement sample of size sigma bar. So this is the sample T11 to TQW, where sigma bar we write as Q and W. Q is the number of queried blocks and W is the width of each block, and G is some abelian group with Gaussian addition. And from this sample we generate a pseudorandom sample, A sigma, where sigma is Q into W minus 1. We generate this sample in the following way. For each block of width W in T sigma bar, we get a block of width W minus 1 in the second sample, S sigma. So how do we get it? We get S11 as T11 minus T1W. S1, likewise we get SW minus 1 as T1W minus 1 minus T1W, and this way. So the question that we try to address here is, let us consider a truly random sample with replacement sample of the same size as S. So the question that we try to address here is S a truly random sample, pseudo-random sample? What is the total variation distance between S and R? So our result is that we obtained, we have shown that the distance between, the total variation distance between S and R is this. And for the special case when W equal to 2 and the group is 0R to the N, we got improvement over this general result. This is given by this one. And for variable width case, for the case where the query blocks do not have the same size, each block has different size, we get this bound. So in the first case, this bound is tight, we have shown it through an attack. And in this case, we have improved recent Crypto 2017 result by Guy, Wang and Tesaro. So this is in a nutshell our result in the paper. So what are the applications? First, let us see that this method can be viewed as this type of construction, XOR PKW type construction in case the block cipher. So the construction is this. We are given a message of x length n minus s. W is a parameter and s is log of w. And we generate and the construction gives output in this manner. So this thing can be compared with TIW. This one is TI1, this one is TIW, and this one is TIW minus 1. So this is the T sample, and from here we get the S sample by XORing. So we are XORing TIW with TI1 and we get SI1, and likewise we get SIW minus 1. To set our results into this cryptographic security context, we just state some regular security definition. So this is a random function chosen randomly from the set of all functions from M to P. 0, 1 to the M to the 0, 1 to the P. This is the random permutation chosen from the set of all permutations over 0, 1 to the P. A is a distinguisher, and F is a keyed function from 0, 1 to the M to 0, 1 to the P. Then the PRF advantage of F can be written as this way, and the PRP advantage likewise can be written in this way. We assume without loss of generality that A doesn't repeat its queries, because once the random choice is random key is chosen, if adversary gets repeats its queries, then it gets the same answer. So, and we consider A to be deterministic since we are considering information theoretic security. So we consider A to be computationally unbounded, and so A can run with the base random points, and it knows everything, so it can be considered to be deterministic. So when A sends Q queries, Q1 to QQ, and it gets XQ as an answer when FK is the oracle, and gets RQ is the answer, RQ as answer when the random function is the oracle. So we denote the distribution of x1 to xq by PR sub x, and this distribution as PR sub r. So then the advantage of the function, PRF advantage of the function can be written in this way. So this relates the statistical distance between these two distributions with the advantage of PRF advantage of it. So as an application, we consider this XOR P EK construction, and we have this result. So under this setting, our result can be shown to have application in this manner for this construction. For XOR PEK, its PRF advantage is bounded by this quantity, and for the variable weight case, we have for non-respecting adversary, its PRF advantage is bounded in this way, where Wmax is maximum of the widths of the queried blocks, and okay. And now for the CENC authenticated encryption, which can be described in this manner. Our result implies the security of CENC, and this improves query range, the range of queries which was proved by Iwata and others from this to n over 1 plus root 2. So they proved it omega into sigma bar less than equal to n over 67 up to that much query it is secure, and we have shown that it is secure there up to n over 1 plus root 2. So this is an improvement, and we have also proposed improvement of GCM in the authenticated encryption standard. So GCM is a nonce-based authenticated encryption, and it provides path-bound security. It's the Caesar competition aims to get better constructions than GCM. So what we have proposed is this construction. EK is the underlying random permutation, which is what the block cipher. H is the hash key. M for L message, L block message, M, and nonce P of this size. S is such that the maxima max L is less than or equal to 2 to the S minus 1. So S is specified, and so the encryption is this. For each MI, we get CI as MI plus EK, I S-bit representation of I plus, or this will be L, S-bit representation of L minus 1. So we have one more block cipher called the GCM standard GCM construction, and the tag is computed in this manner. So here also it will be L. So we have one more block cipher call, and for this improved, so we term this construction MGCM. For MGCM, we have this result on its PRF advantage. So this is for the encryption part. The other part can be also shown with Wagman-Carter argument. So how can we prove our result? It can be proven by two methods. One is the mirror theory, and the other is the chi-square method, which has been recently introduced. Mirror theory is this can be explained in this manner. So fix some sigma, and let C be this set. It's a subset of all possible ij's with ij ranging from 1 to sigma, and let S be all possible blocks P1 to P sigma, which are each from 0, 1 to the n, and such that Pi plus Pj equal to Cij for all ij belonging to C. So C is fixed. So the question is, what is the maximum number of possible such solutions? This type of solutions. So mirror theory has provides a lower bound for this the size of the set, and it also implies an upper bound on the statistical distance between S sigma and R sigma, which has been shown by Katarine. It's quite powerful in terms of implications. With the mirror theory, optimum security for many constructions, EDA, EW, CDM has been proven recently, and but it is quite complex, and some of the states are really difficult to understand. Underlying theory is quite heavy and lacks necessary details in some parts. So compared to that, chi-square method, which has been recently introduced by Lai, Wang and Tesaro in 2017, it's been used to prove full security of XOR P2, the sum of two random permutations. It has also been applied for improved security proof of EDA. Incidentally, STAM long back used this method to show pseudorandomness of truncation of without replacement sample construction in a purely statistical context. The theory, underlying theory is pretty much transparent and elementary and easy to understand. So we get some sort of confidence in the theory, this chi-square method. seems to have potential, further potential for applications. Recently we have used it to show full indifferential insecurity of multiple random permutations. So what is this method? Suppose X is a distribution, X1 to X2, and Y is another distribution over some sample space. And we define this, we denote this conditional distribution by this one, in this way. And where we take X1, X0 to be this thing. Conditional and X0 to be this thing. And similarly, we define for the distribution Y, we define similarly. And then the chi-square distance between these two conditional distributions is defined in this manner, where omega xi minus 1 is all xi belonging to the support of xi, such that superscript I is x1 to xi, so xi is all those xi for which superscript I belongs to omega I. So to apply this method, one thing should be checked, that the support of yi should contain support of xi, which is omega I, for each possible I. This is somewhat subtle condition, but it has to be checked so that this chi-square distance becomes well defined. Otherwise, it is not well defined. So the result of Dai, Wang and Tisserand into 2017 is that they gave an upper bound on the statistical distance between two distribution x and y by their chi-square distances, expected value of chi-square distance. And the ingredients of the proofs are quite elementary. It uses Pinsker's inequality, chain rule of J divergence, and Jensen's inequality. It's a simple proof. And this gives a pretty useful bound on the statistical distances between two distributions. Now, how can we use this method to obtain our result? So we have one random experiment, that is a random without replacement sample, and this is the sample that we try to prove as pseudorandom. We are sampling T1 Tij's from in a WOR manner from G and constructing Sij's. So this is the experiment. And so here are some observations. Both R and S have the same sample space, G to the Q into omega minus 1. They don't have the same support. The support of R is obviously entire G to the Q into W minus 1, whereas Tij's are distinct. We are sampling Tij's without replacement manner, so Tij's are obviously distinct, which implies that Sij's are not equal to 0 for all ij. And also, for any I and j not equal to j dash, Sij is not equal to Sij star. So the supports do not match. So what we do is that we consider an intermediate distribution, and for this intermediate, what is this distribution? This is we are sampling each block, each W minus 1 block in a without replacement manner from G minus 0. So this becomes quite similar to S. And the way we prove the statistical distance between these two distributions is by using triangle inequality. We first show that the distance between U and R is bounded by this quantity. This is easy to prove because U and R are identical until for some ij Rij equal to 0, because 0 doesn't appear in the distribution for U, and for some I and j not equal to j bar, Rij not equal to Rij bar. If that happens, then these two distributions are distinct for these two events. So probability of this this first event can be bounded as q into w minus 1 over n, and probability of the second one can be bounded by this quantity. So if we sum these two, we get this quantity. So this part is bounded. Now what about this part? This is where we use the chi-square method. So once we add up these two, we get the required result. So for the first part, we extend the original distribution S to X. This is not very difficult to see. This is the original distribution S. How we are getting it? We are sampling T without replacement manner and constructing Sij as Tij minus Tiw for each I and j. And what we do is that at the end of each block we append Tiw. So for original distribution Si, we had only Si1 to Siw minus 1, whereas in case of Xi, we append Tiw. So we are kind of giving out more information. So from this information, one can easily get Ti1 to Tiw, because if you add Si1 with Ti1, you get Tiw, you get Ti1. So we are extending S to X, and S is the marginal distribution of X, and we return X. So what we see from here is, first consider a function rho from G to B omega to G to B omega, where it takes Z1 to ZW and returns this value. So it is easy to see that this is a permutation from G1, G to BW to G to BW. So, and for this permutation, rho of Xi becomes Ti. Because if you give Xi, it adds Si plus 1 with Tiw, that is Z1 plus Zw, and it gets Ti1. So likewise, if it adds each component with Tiw, it gets back the entire Ti. So rho Xi is Ti, and we extend it to all the Xi's by component wise applying rho. So rho of Xi, rho star Xi equal to Ti. And after doing all this, what we get is that the value of this conditional probability of Xi given Xi minus 1 under the distribution X is given by this quantity. And where, of course, if you apply rho Xi, you get Ai, and rho star Xi minus 1, you get Ai minus 1. So as Xi are sampled according to distribution capital Xi, Ai are sampled according to distribution capital Ti. Okay. So this way we get this value, Xi given Xi minus 1, and similarly we extend U to Y, and the random experiment is slightly involved, so we don't explain it here. The message from here is that from this experiment we get the distribution of Xi given Xi minus 1 under the distribution Y as this quantity, where this is some cardinality of some set which depends on Xi minus 1. So it's a, for fixed value of Ui, it's a function of Xi minus 1, where Ui is the first W1, W minus 1 components of Xi, and this is the last one. And this value is greater than 0, which means this chi-square distance is well defined, because we have non-zero value in the denominator. And since it's a function of Xi minus 1, after some calculation we get this quantity, where C and D are these expressions. And it's a function of Xi minus 1, so once we sample Xi according to Xi minus 1 according to distribution Xi minus 1, we get a random variable. With the expectation we can take over the distribution Xi minus 1, and it gives this quantity. And finally we computed D equal to X of expectation of this quantity. So this becomes variance of this random variable, and this is the final expression that we get. So after simplification, we get this value, and this gives upper bound on x and y, because s and u's are marginal distributions of x and y. This is upper bounded by this quantity. So we finally get an upper bound on the total variation between s and u. And for this special case, we get input value of
you should go to your conclusion, please.
Yeah. And for variable width case, the experiments are almost similar, and the result can be obtained in a similar manner. So that's all.
Thank you.
Yeah.
Questions or comments? Okay, I have a short question. Do you think that this chi-square method can also be applied to some other construction in the future?
Yeah, we are trying to apply it on various other constructions where already mirror theory has been applied. So we are trying to see. Not everywhere can we apply this method that we have observed, but in some cases possible.
Okay, thank you. So let's thank the speaker again and all speakers of the session. We now have lunch, so be careful because the lunch is 10 minutes shorter than usual. So the next session will start at 1:15.